Okay, so the first problem, you were looking at a problem where I had set it up and it's 1-to-1. So what you do is you take the y values, so think of that parabola. You need something in your head to think about. Think about the parabola with the two y values that were equal and the x values were not. So you're checking if I set the two arbitrary y values equal to each other, will the outcome be that the x values have to equal each other? So I do this. I set the two y values equal to each other, and I get this formulation, x1 plus x2, with x2 as the second component, equal to y1 plus y2, and y2 as the second component, by just doing the matrix multiplication. Setting equal the equations, the components, I get two equations. And when I solve them, I get a unique solution that tells me that x1 has to equal y1 and x2 has to equal y2. That gives me only one answer, that x has to be y. So by the definition, we have that if the ax equals ay, then the x had to equal y. That's the definition of 1-to-1. So this particular matrix is 1-to-1. And you guys were quiet and worked through this really quickly, so I hope this is really well understood. So the second one, I think a few of you struggled because you didn't see it. If you do the same work, you really get one equation. You get x1 plus x2 is equal to y1 plus y2. And if you look at it, you think, well, I could have x1 equal y1 and x2 equal y2 and it'll work. The problem with that is there's more than that as a solution. You could have x1 equals, this does not necessarily mean that's the only solution. You could have, for example, x2 equals y1 and x1 equals y2, and the sums will end up summing up to the same thing, but the initial points were not equal. So because there's more solutions than just x equals y, this particular matrix is not 1-to-1, or this transformation is not 1-to-1. So how do you make up these 2-by-2 matrices? I was watching you work, and I think you guys were just messing with the numbers, but since I know your book, there's a theorem in your book that says 1-to-1 matrices have to be invertible. And there's another theorem that says that invertible matrices have non-zero determinants. So I connected the two, and I just made up something that has a non-zero determinant, and just checked, is it 1-to-1? And indeed it was. Came up with the same work. So that x1 is y1 and x2, and that's the only solution possible. What about a non-1-to-1 example? Well, the theorem in your book says it's invertible if and only if it's 1-to-1. So I can use the same trick. I could say, okay, I don't want it to be invertible, so I'm going to set up some letters. I'm going to take the determinant. If it's not invertible, then the determinant has to be 0. So that gives me a formula for choosing the A, D, and the B, C. And so I just made up some examples. I just chose D equals 6 and B equals 3. I just chose some numbers. And I get that the determinant is 0, but is it 1-to-1? So popping it into the same kind of procedure again, I set the AX equal to the AY, and I get exactly that one of the equations wipes out, and I'm left really with one equation and two unknowns inside there. And what that tells me is that I could just make up some numbers, kind of like I did for the first problem, but I can just make them up. They're a little bit more difficult to make up. So I had to play around a little bit. I got this to be 16, and then I looked over on the other side and I made some choices to get that to be 16, but those numbers weren't equal in any way. So number 2, I'm going to let you play around with that one a little bit. So, and then we'll go over that one.